Welcome back. In the last class, we have gone through series regulator block diagram and the corresponding circuit diagram, and I need to explain the flow chart, how it is controlling your output voltage, right? I just explained that if V0 is changing, the loop is coming into picture, but op-amp should be configured in negative feedback, you will get V0 constant. Let me explain the same thing using flow chart. Okay, I hope you copied this. Okay, same thing I'm explaining using flow chart. That is easy to remember and easy to understand as well. Now, due to any reason, just listen, due to any reason, if V0 is increasing, when V0 increases, then your V0 is sampled, right? Your V0 is sampled through beta network. Beta network is nothing but your feedback sampler. Therefore, R2 divided by R1 plus R2. Therefore, beta V0 increases. When beta V0 is increasing, that is what is going to compare with what? That is what is going to compare with op-amp. That is what is your reference voltage. Voltage at minus increases. When voltage at minus is increasing, what about your op-amp output? Your op-amp output is nothing but your VB, the voltage at base. Voltage at base decreases. When voltage at base is decreasing, then tell me, what about your VBE? VBE decreases. When VBE is decreasing, what about your IB? IB decreases. When IB is decreasing, what about your IE? IE decreases. When IE is decreasing, what about your IL? Your IL decreases. When IL is decreasing, what about your V0? That is what is going to control V0. Therefore, V0 decreases. Then overall, whatever it may be, your V0, your output voltage, if due to any reason if V0 is changing, negative feedback is coming to picture and making V0 constant or making V0. Therefore, this is almost constant. Okay. Therefore, the V0 change is due to either line voltage or load change, but ultimately the negative feedback is coming to picture and then making V0 constant. But again, this is sequential explanation, but practically this will not happen. As I told you before, right? It is not that your V0 is increasing, negative feedback is coming in and making it constant. That will not happen practically. As I told you, if V0 is trying to increase, immediately negative feedback will come into picture and then making it not to increase, right? Then it will make V0 almost constant. Okay, and it depends on, let us say your load is changing suddenly, then definitely V0 changes. Then it will take some time to settle and then it will give you constant output voltage. This is what people say loop settling time. That is because of the loop bandwidth. The loop bandwidth will be lower to get more phase margin or gain margin. I will not go into those details. When you enter into higher education, when you design a regulator, right, a series regulator or LDO, low dropout regulator, instead of BJT we can use MOSFET, then you'll understand what is loop settling time, means how much time it is taking to settle or how much time it is taking to correct your output voltage if there is a sudden change in output voltage, either due to line voltage variation or due to load variation. Okay, those things I will not speak, it's not required. It is like DC voltage variation. Due to any reason, if V0 is changing, right, increasing or decreasing, that loop will come into picture and then making it constant, assuming that the V0 changes low frequency variation. Okay, fine, or DC variation due to load variation or line voltage variation. You can take the flow chart, then I'll explain shunt regulator. Okay, let me explain shunt regulator completely in one shot, like block diagram, circuit diagram, flow chart, all together one shot. Let me try to adjust. Else we have to write first block diagram, circuit diagram and flow chart. Whatever we did in the case of series regulator, similarly we can do for shunt regulator. Okay. Practically people go for series regulator. Okay. That is what we say LDO, low dropout regulator. Whatever line voltage you have, because nowadays the power supply is decreasing, right? When power supply is decreasing, I am requesting for V0, let us say 1 volt, but input is also 1 volt. Input is 1 volt, how can I get on 1 volt? almost the drop VCE, right? Almost I want VCE to be 0. That is in the case of BJT, right? Which is 0.2, less than 0.2 we cannot go. Else it will enter into saturation. When it is entering into saturation, it will not act as a control element. If you want to use your BJT as a control element, it should be in active region. Then only your VB will control IB, IB will control IE. Else there is no relation between IB to IE. Remember, that is what is called biasing. We need to bias the circuit such that your transistor will be in active region. That is compulsory. Therefore, if active region BJT is in active region, the VCE, collector to emitter voltage, definitely should be greater than 0.2. Then 0.2 voltage is dropped here. Then whatever line voltage you are applying, let us say we are dealing with low voltages, then 0.2, line voltage minus 0.2, you will get output voltage. In olden days, whatever power supplies you are having, then let us say power supply is 15 volt, I can get whatever voltage I want. But now the power supply, the line voltage itself is very less, let us say 1 volt, but I am expecting output is also almost 1 volt, it is not feasible. That's why people go for low dropout. I want low dropout, then whatever voltage you are having, entire voltage should come. Therefore, instead of BJT, if you use MOSFET, the MOSFET VD sat is depending on VGS minus VT. Not like BJT. In the case of BJT, that is 0.2, almost fixed. But in the case of MOSFET, we can go to almost like 50 millivolt, or I can say 60 millivolt or 100 millivolt. Therefore, with lower dropout, you can get your output voltage almost equal to line voltage. Okay, that is fine. Now, shunt regulator. Okay, case 2, shunt regulator. Just listen, don't write. Second one, shunt regulator. The control element will be in shunt with respect to input to output. Okay, just listen, I will give you a block diagram. The block diagram is, this is the control element. Now the control element is in series, sorry, in shunt. Then this is what is your load, and this is what your output voltage V0, and this is your load current. Let us say this is your RL, load RL, V0 is equal to IL into RL. Earlier people used to use GNR diode as control element, but now I am using op amp. Okay, but the GNR diode part I will explain, which is nothing but shunt regulator, because GNR diode is in shunt to your output to input, but that part I will explain from chapter 5, diode circuits. Okay, then the control element will get control signal from comparator or error amplifier, comparator or error amplifier, right? And the comparator will get, it is going to sample, therefore this is sampling network, this is sampling network, your output is sampled, then giving it to the comparator, and it is going to take the reference voltage from reference generator, then it is going to give control element or control signal, this is giving control signal, then whatever line voltage, let us say this is what your line voltage, right? Then it is going to take shunt current, it is going to take shunt current ISH, and it is going to give series current IS, source current or line voltage IS is equal to ISH plus IL, right? Now let's see how it is controlling your output voltage. Due to any reason, if V0 is increasing, then the sampling network it will excuse me, yeah, if V0 is changing, then your sampling network will sample the V0 change and giving it to comparator. Error amplifier is going to compare with the reference voltage. Then if there is any deviation from your output voltage after sampling with respect to reference, that is what is going to give you a control signal. Then the control signal will give it to the control signal will be given to control element. Then it will take more shunt current or it will take less shunt current to control the current which is what is flowing through load current. Therefore ultimately it is going to control V0. Whatever I explained here, right, I can explain through circuit diagram. Right? Now the circuit diagram, if you take circuit diagram, just this is what is our control element, this is your control element, your BJT is nothing but a control element. Now this is what is our load, this is your RL, and this is your output voltage. V0 is equal to the load current IL into RL, right? And we are going to sample it through sampling network. Sampling network is known to you, simply R1, R2. Then here this is what is going to have the error voltage or error amplifier. Then the sampling voltage will be coming from R1, R2 combination. Then this is what is our line voltage, right? Then the reference, whatever reference, typically I told you, right, you can use Zener diode. That is the reference. Now you can say this is what is our line voltage, right? And this is what is your VZ, which is your reference voltage, and this is your R. Okay. Now which is minus, which is plus? You can neglect the current which is flowing through it. And now this is what your shunt current. This is your shunt current ISH, and this is what is your source current IS. IS is equal to ISH plus IL. Okay, neglecting the current which is what is flowing through R1 and R2. Now if you listen, tell me which is minus, which is plus. Right? Now let's see. We don't know. Let us say this is what is minus and this is plus. Let's see. And this is nothing but your collector. This is base, collector, emitter, and this is what is your sampling network. This is your beta V0. Okay. Now let's see. Okay. Now due to any reason, if V0 is increasing or decreasing, anything is fine. Let us say V0 is increasing. Due to any reason, if V0 is increasing, the same output is sampled, beta V0 increases. If beta V0 is increasing, voltage at plus is increasing. When voltage at plus is increasing, what about output voltage, which is nothing but voltage at base? This is nothing but VBE, right? This is basically VBE. This is your VBE, right? Then if voltage at plus is increasing, then voltage at base is increasing, means your VBE will increase. When VBE is increasing, what about your IB? IB also will increase. This is basically your IB, right? Op amp is giving base current, right? How much current your transistor is asking, then your op amp will give that. When VBE increasing, then your base current will increase. When base current is increasing, then your collector current will increase, which is basically shunt current. When shunt current is increasing, assuming that IS is constant, when you say IS is constant, that is not the variation, then if ISH is increasing, then definitely IL will decrease, because your source current is constant. When source current is constant, then if ISH, if it is taking more current, but input current is constant, then your IL will decrease. When IL is decreasing, your V0 will decrease. When V0 is decreasing, you can say your V0 is almost constant. Your V0 is almost constant. This is what is your variation, right? And again, whatever I explained here, right, you may have doubt, how can you say IS is constant, right? Remember, line voltage variation or load variation ultimately changed V0. If V0 is increased, everything kept constant, but V0 is increased. Internal disturbance or line voltage disturbance or load voltage disturbance, load variation disturbance ultimately affecting your V0. Let us say V0 is affected and then now everything is kept constant. Then the loop will come into picture, it will correct your V0. Then in that case we have to, when you want to see when V0 is increasing, then we have to keep everything constant only, because V0 is already changed because of the changes. Then already change is done from input or the load or internal disturbance. Then remaining things we have to keep constant, increase and then constant. Then we need to see if V0 is increased, then how the loop is coming in and controlling it. That's why your IS is constant. When I say IS is constant, then if ISH is increasing, then your IL will decrease. Therefore, IL decreases, then V0 decreases. Therefore, V0 will be constant. That is important point. That is the keynote. Okay. Now, whatever I can explain through flowchart. But if you observe clearly, wantedly I did something which is a blunder. It is not a mistake. Therefore, you'll get some V0 almost constant or some variation. There is a blunder. Blunder means complete circuit is wrong, because I missed something. Whatever I explained, V0 increases, sampling network will sample, it will control. By control signal, control element will take more shunt current, then your load current will decrease, V0 decreases. Yes, all are fantastic, right? And all are convincing you, right? Yes, definitely convincing, right? Because of negative feedback. V0 is increasing, beta V0 is increasing, voltage plus is increasing, voltage base is increasing, VBE is increasing, IB is increasing, IC is increasing, shunt current is increasing, load current is decreasing, IL is decreasing, V0 is decreasing, and then saying that V0 is constant. But it is a blunder. Theoretically, that is what? Theoretical knowledge versus practical knowledge. If you implement the circuit on breadboard, and if you try to see the output voltage, if you change your line voltage, and if you see output voltage, your output voltage also will change. There is no regulation. Why there is no regulation? Because of blunder. What is the blunder or the mistake? If you observe clearly, the line voltage whatever we have given here, that is entirely that is what is given to your output. Whatever you have, the rest of the circuit, this is nothing but what? Redundant, not used, not useful at all, because your line voltage is exactly sampled and given to your V0. Right? If line voltage changes, definitely V0 changes. This is what is your primary control, which is what is going to change your V0. Line voltage, it is short circuit, it is a wire. It is a wire, output is connected to input, but whatever you have, whatever you sample and you connect, no use. Similarly, the line voltage is having simply short. Your V0 is equal to your VI, line voltage. If line voltage is changing, definitely your V0 will change. All the explanation what I gave now is not valid. But whatever I am saying, increases, decreases, convincing, right? That is what I am saying. Qualitative analysis, theoretical knowledge versus practical knowledge. Once you implement this circuit practically, and if you see the voltage V0 with respect to line voltage, your line voltage will be, your output voltage will be tracking to your line voltage. Therefore, if there is a change in the line voltage, your output also will change. But we want regulation. Even though line voltage changes, your output voltage to be constant, right? The blunder or the correction is people put resistor. There should be series resistor. This is what your RS. Okay. If the line voltage is increasing, to make output voltage constant, the increase in line voltage will be dropped across RS. The increase in line voltage will be dropped across RS. Therefore, similarly, there should be a series resistor, right? The series resistor, when you keep, this is what is our series resistor RS. Okay, now this is correct. See the small correction making the circuit regulator, else it is not a regulator. The series resistor is important, because earlier we don't need any series regulator in the series resistor in the case of series regulator, because the BJT was a control element and that was in series to output to input, that will control. But now here we need a series resistor. Okay, that's fine. Now whatever I explained, valid, provided your line voltage is not directly shorted to your output voltage. Very important, right? That is what? Theoretical knowledge versus practical knowledge. Theoretically, even though it is convincing, but practically it may not work. Whatever I explain, let me explain through flowchart, right? That is nothing but, let us say, your V0 is increasing due to any reason. If V0 is increasing, then when V0 is increasing, then beta V0 will increase. Beta V0 increases. Actually, whatever terminals minus plus you have taken, that is valid. It is controlling it, right? Therefore, it is in negative feedback. Your op amp is in negative feedback, right? Then when beta V0 is increasing, then voltage at plus increases, that non-inverting terminal voltage. When voltage at plus is increasing, the output voltage of op amp, which is nothing but VBE, your VBE will increase. When VBE is increasing, what about your base current? Your base current also increases. When base current is increasing, what about your collector current? Your collector current also increases. When collector current is increasing, that is nothing but your shunt current. Your shunt current is also increases. When shunt current is increasing, right, then your load current will decrease. Your IL will decrease. When IL is decreasing, then your V0 decreases. When V0 is decreasing, therefore negative feedback is controlling your V0, and this is almost constant. Therefore I told you, right, let me try to explain block diagram, circuit diagram, flow chart in one snap or one sheet of the board. Done. You take it, then we will see. I can say the concept related to regulators or power supplies is over. Now we will see the problems with that. It is done. Okay. And the problems related to regulators are straightforward and then easy. Okay. Let's see. Sorry, mic is under mute, but not required. I'm looking for problem number 24, and this is what is the problem, and asking for the value of R. Even though audio is not there, you should be able to get it from video. Okay. Anyway, I didn't explain any concept. I've just taken the circuit, and V0 is given, which is 9 volt. That is what is your regulator output voltage, and line voltage is 12 volt, and reference voltage, that is what is generated from GNR diode. Then the GNR voltage is 4.7. When GNR diode is under breakdown, it will act as a battery. The battery is nothing but 4.7. Then R is chosen such that the GNR diode is in breakdown. That is what is the biasing. That is what is done. Then asking for R. Tell me what to do. How will you solve? Remember, this is nothing but op-amp problem. If you treat this as op-amp problem, tell me, is op-amp in negative feedback or positive feedback? Is op-amp in negative feedback or positive feedback? Definitely it should be negative feedback. If op-amp is in negative feedback, virtual ground concept is valid. Then virtual ground concept is valid. What does it mean? The voltage at this point. Now what is your reference voltage? Your reference voltage is 4.7. Therefore reference is 4.7. Therefore voltage at plus is 4.7. And what is voltage at minus? Voltage at minus is also 4.7. This is also 4.7. This negative voltage is trying to track to your positive voltage to make error voltage almost 0. Then when this is what is 4.7, we know that this is nothing but beta V0. This is nothing but you are sampling your output voltage through beta network. Therefore this is what your beta network. What is beta V0? Beta V0 should be equal to 4.7. I think problem is over. Therefore tell me what is beta. Beta is nothing but R2 divided by R1 plus R2. R plus 1K into V0 is equal to 4.7. Then tell me what is this. Then if you take to right hand side, R into V0 is equal to 4.7 into R plus 4.7K. Then if you take this to here, what are we going to get? And then what is the V0? V0 is nothing but 9, right? Therefore 9 into R is equal to 4.7 into R plus 4.7K. Then tell me 9R minus 4.7R. 9R minus 4.7R is equal to 4.7K. Therefore 9R minus 4.7, can I say 4.3? Yes. Therefore 4.3R is equal to 4.7K. Then R is equal to 4.7 divided by 4.3 kilo ohm. What is this? What is 4.7 by 4.3? You calculate, you will get it. Is it objective type or subjective type? This is what is what? This is nothing but fill in the blank. We need to fill it. Therefore tell me what is 47 by 43. Approximately 43 ones are 1 point. Then you'll get 4, 0, approximately 1 point, right? 0, if you put 0, it will become 40, approximately 1.0, or you can say it is approximately, if you calculate, 1.09 or 08 kilo ohm. Sorry, 1.01. Okay. And if you want exact answer, we can get exact answer also. 47 divided by 43. 1.093. Okay. Sorry, this is 1.093 kilo ohm. At least you give 2 decimals or 3 decimals if the problem is associated to fill in the blank. Okay. The answer is 1.093 kilo ohm. Now the last problem for this session, problem number 25. For the voltage regulator circuit shown, the input voltage is 20 volt plus or minus 20% and regulated output voltage is 10 volts. Assume that op amp is ideal. For a load drawing 200 milliampere, the maximum power dissipation in transistor Q1 is, okay, let's see. Is this over? Done? $30 seconds. After that, we'll see problem number 25. Problem number 25. Right? Circuit is given. Okay. Circuit is, again this is series regulator, okay. And load is also given. This is RL and this is V0. This is R1 and R2. Then reference voltage Vref. Okay. This is having ground. And this is your line voltage Vi, and Vref is equal to 4 volt. This is plus, minus, and this is what is Q1. Okay. Now what is given? Input voltage is 20 volt plus or minus. Therefore your input is 20 volt plus or minus 20%. Your input voltage is changing about 20, but change in the input voltage is 20%. Kind of ripple. And regulated output voltage is 10 volts. V0 is also given, that is 10 volts. Assume that op amp is ideal. For the load current IL, what is IL? IL is given, which is 200 milliampere. Okay. Then the maximum power dissipated in the transistor, the power which is what is dissipated, and that to maximum is what? It is also fill in the blank. GATE 2015, 2 marks, set number 2. Okay. Now, he is asking what is the maximum power dissipation across the transistor Q1. Okay. This is nothing but your series regulator. Okay. That's fine. Now, how will you calculate? First of all, what is power dissipation? Power dissipation across the transistor, right? Power dissipation across the transistor is, we know that this is nothing but, this is collector, this is emitter, this is base. I told you, right? The current which is what is flowing through R1, R2 can be neglected. Whatever current which you are getting, right? This is nothing but your emitter current, that is what your load current. Let me say directly IL. And the voltage what you have across collector to emitter, let me call this as VCE, collector to emitter voltage. You have the drop, therefore input voltage minus VCE is nothing but your output voltage. Okay, the VCE will be adjusted automatically because of the control voltage what you are getting from your op amp. to get output voltage constant. That we know already. Therefore, tell me what is power dissipation across the transistor Q1 is nothing but VCE into the load current IL. You know already load current, that is 200 milliampere. Now we need to find VCE. What is VCE? VCE is nothing but voltage at collector minus voltage at emitter. That is nothing but your collector to emitter voltage. Voltage at collector minus voltage at emitter into IL. What is voltage at collector? Voltage at collector is nothing but your VI. Therefore, that is nothing but your input voltage VI. And what is voltage at emitter? Voltage at emitter is nothing but V0 into IL. Right? Therefore, what is VI? VI minus what is V0? V0 is constant. That is 10 volts into IL. What is IL? 200 milliampere. Whatever may be. That is constant. Now I want power dissipation across the transistor maximum. The maximum power. Therefore, then VI minus 10 into IL. It should be maximum. Tell me when is this maximum? According to mathematics, your IL is constant, that is given 200 milliampere. Therefore, only the variable is VI. When VI is maximum, then PQ is maximum. Therefore, that maximum will be going to your VI max minus 10 into IL. Right? What is VI max? 20 volt plus 20%. That is what is the maximum voltage you can see at the input. Right? Therefore, what is that? Your VI max. Therefore, this is what is equation 1. To find VI max. To find VI max. What is VI max? VI max is equal to 20 volt plus 20% of 20 volt. 20% of 20 volt. That is what is your maximum voltage. Right? Therefore, what is it? 20 plus what is 20% of 24, which is nothing but 24 volt. This is nothing but your VI max. Then 1 implies, tell me what is PQ1 max? PQ1 max is equal to, VI max is 24, 24 minus 10 into what is IL? 200 milliampere, which is 0.2 ampere. Therefore, 24 minus 10, 14 into 0.2 ampere, which is nothing but what? 2.8 watt. This is what is your answer. What is the answer? The maximum power dissipation across the transistor is 2.8 watt. And if you know that your input maximum voltage is plus or minus 20% about 20 volt, then we have to choose the transistor where the transistor is having power handling capacity, which is 2.8 watt. Let us say if you choose 1 watt transistor, then if you vary your input voltage like plus or minus 20% about 20 volt and output is 10 volt, your transistor will be burnt because it cannot handle 2.8 watt if you choose only 1 watt transistor. Then if it is 2.8 watt, it's better to have some margin. Therefore, it's better you choose 5 watt transistor or whatever more than 2.8 watt transistor. Then if you use 5 watt transistor, maximum we are seeing 2.8 watt. Due to any reason, if the input voltage is further increased, let us say, then we have some margin. That is what people say reliability validation or RV margin. Therefore, your transistor is having some margin. Therefore, whatever may be the maximum power which is dissipated across the transistor is 2.8 watt. Then the maximum power handling capacity by the transistor should be more than 2.8 watt. Okay. I hope everybody understood the procedure. First of all, what I did, I just calculated the power dissipation. Right? That is nothing but voltage across the transistor and current through the transistor. Then we understood what is VCE, and then finally to get PQ and max, it is coming to VI max minus 10 into IL, and we found VI max and then substituted and then we got 2.8 watt. Okay, that is the answer. Sorry, again it was under mute. I didn't say anything. I told that after this we will continue for next topic. The next topic is triple FI timer. Once triple FI timer is over, then we'll go for chapter number 5. Okay. Thank you so much. Please continue.